My name is Dr. Shobhusha Sen. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bouquet is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that you'll be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we'll be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen. Students, very good morning to all of you. Again, welcome back to my class. In the last class, I have actually introduced the basic ideas of quantum mechanics 2 and how it is connected with your entire physics 2 course that you are now undergoing as a computer science and IT student. I mentioned the importance of each topic that is present in your course in the second year physics course, and I also mentioned, which is very important to note, this course is indigenously made for you. You have kept topics which are aligned to your requirements only. We have kept the latest computational technique called quantum computation, which is the future of computation. When you do high-end computation, it is quantum computation. Google has come up with that. So some of you will be working in Google. So let's get introduced with it, okay?
you'll be introduced to the latest of the areas called latest of materials, okay, which are making the building blocks of the most modern computing devices, electronic devices. They are called nanomaterials. So that introduction, those things are also in your course. So in general, the topics apart from electromagnetic theory, the topic kept in the physics 2 course are highly modern, highly timely, and it is highly inclined to your requirement as a computer science and IT professional. So in your own course, your teachers of department will maybe be focusing on the coding part a bit, but the hardware part, or what is how they operate, how they work, or in as a computing professional later on also where you do your coding, what are the areas of application. Suppose you are learning the latest coding, you are learning Python as a language, but we use Python language also as a physics people in the design of nano electronic devices. So there we solve a lot of calculation, we do visualization of electronic devices at the nanoscale, which is very hard to see, okay, uh, and there you do coding. But so your Python coding ideas, your algorithms is being used by us in actual purpose. There are many more applications like this also. Actually, Python is a language which everybody is learning now. We are also learning, you are also learning. So there is no never-ending process. So that means actually it has become important because everybody is using it. We are using it. Your mechanical friends, electrical friends in their domain will be utilizing it. And your job as a coding professional, as a software professional, is to provide that support. So areas are coming stronger so that we can all of our idea can bridge together and do some wonderful thing. So that is a majority of the course content, is to learn the latest topics of physics. That is and it all actually these most modern topics of physics are all connected with the quantum ideas. So I have chosen quantum mechanics 2 as my first topic. That is also your module 1. This is me. You know me also. And you see, what I tried to tell you in your previous class is that uh, we'll be learning quantum mechanics too, but this needs some fundamental, some foundation, some recap. Ideally, you have learned quantum mechanics 1, so you are supposed to have some very basic knowledge about the theoretical part of quantum mechanics. That is how what is quantum theory, how everything has came up. Okay, from the basic idea of Max Planck, whose picture you can see there, from his idea actually how entire thing cropped up. Okay, so how from the ideas of Max Planck this entire concept got developed. So this thing I have and it is a story of 27 years from 1900 to 1927, I often tell. So that story is expected to be with you because those theories are now being applied in quantum mechanics too. And whatever you learn, the technique you learn quantum mechanics too, that will be applied in quantum computation, solid state physics. Okay, so these are all connected approach. So what I told you that last day I have taken a small quiz of you to remind you of your first year knowledge. And today I shall do another technique actually to make you remember whatever or what are the essence or what are the major important ideas of first year. So that I will make a quick recap now so that you can it becomes easy for you, because without some of the basic concepts of quantum mechanics 1, okay, that foundations, we cannot do anything in quantum mechanics 2. So let me get into that quick recap. And this is he's the most important person, Max Planck. He has actually changed the physics. Okay, that his idea, he was doing a simple job of thermodynamics, as you know. I'm just quickly telling you how everything came up. In 1900, he explained black body radiation, where a black body was heated and emitted energy was measured and plotted, and people wanted to calculate, scientists wanted to calculate what is the total energy emitted due to the heating of the black body. So total energy emission means you have to do an integration like that, where you integrate a function E lambda. Problem was that in that year, in those years, the right form of the correct form of E lambda was not known because it was an unknown graph to the scientists. It was an experimental graph. So various proposals made, and the correct proposal was made by Max Planck. What Planck did, he has made few assumptions. Okay, And the most important assumption made by Planck was this idea that energy of an object is discrete. He used it for harmonic oscillator. Charge harmonic oscillator is the right term. Energy of an object that tells us energy of the harmonic oscillators are multiple of called h nu. So what Planck did, he has told that energy of an object cannot be arbitrary, it is discrete. Discrete means quantized. So Planck is the first person who used the word quantum, quantized pieces. Energy could be discrete. Later on, everybody followed him. Einstein followed him in his photoelectricity theory. The Bohr followed him in his atomic orbital theory. But what Planck is doing, Planck is pioneer. He is dividing physics into parts. From Planck, a new area of physics begins, the modern physics, the quantum ideas. So we are using 1900 as a benchmark here. Before 1900 is classical, after 1900 as the modern physics. And what you do, we can you see, I just want to remember or tell you how everything got changed. Classically, everybody knows there are two things are there in nature: objects, waves, and matter. Matters means matter may be big object like car, bus, train, tram. We are also matter, and maybe small object like electron, proton, neutron, etc. But to describe them, we use some basic parameter like mass, momentum, size, and shape. Okay, and waves are something else. Waves are like light and sound. So light wave means electromagnetic wave, and sound wave means audio wave. So basically two different domains of waves and matter. So we have been describing matters with mechanics concept, waves with either Maxwellian theory for the waves, which will be again learning, and for acoustic waves some other theory. Now these theories, these ideas tells you the best exhibition of the material property is collision, and best exhibition of the wave property is obviously the superposition. Okay, superposition is the best exhibition of the wave property. Now this and if a wave is incident on a matter, we get a phenomenon that is called scattering. Okay, scattering takes place. Reflection is an example of scattering. Now these ideas are not incorrect. They are good idea. They are correct idea. Problem is that some of these ideas are, there is somewhere it is inherent. Matters are something else. Waves are something else. For matters we learn mechanics. For waves we learn wave theory. And matter wave the mixed situation, as you can see, the reflection or scattering mechanism. Now these ideas got shattered because of the two experiments that was done after 1900. One of them is, as you know, is called photoelectric effect, and another experiment, as you know, is called Compton effect. So we learned for the experiments, photoelectric effect and Compton effect in detail. What they did, they have actually changed the way of people are taking up the matter, the situation actually. What photoelectricity did, just to make a quick recapitulation, it is an experiment where what was happening, the light was being scattered by a metallic metal. Okay, and it is expected that it is just like the normal scattering mechanism, we should get a scattered beam, but the beauty of the experiment was that we are getting electron emission. So this was something unique, something uncanny. So with the classical theory, that is wave incident on a metal, that means in this case matter, will give me scattered beam. That was not the case. Some electrons are coming out. So people so classical theory could not explain it. So Einstein has given the photonic theory. He told that the incident radiation is a stream of photons coming in. Okay, it is just like you see the picture. A photon is coming in, that photon is being absorbed by the electron, single electron. Photon has got some energy, h nu, etc., etc. And if it is energy sufficient for the electron to overcome Coulombic repulsion attraction, then electron will go out, as it is going out in the picture, as you can see there. So this was the concept. Okay, see, photon is coming and it is being absorbed and electron is going out. Okay, so it was very good. It was correct. It was a highly exemplary concept, that radiation means a stream of piece of photons. Light is a collection of energy packets called photons. That has been the pioneering concept of the Einstein. So it tells us, therefore, that radiation can sometimes show photonic nature. Now, what photon is, to give a better idea about photons, okay, later on, one more experiment was done about the, that is the experiment of what Einstein is telling, that a wave can be metal-like. One more experiment was done, that was the experiment of Compton effect. It was done in 1923, as you know. Now the experiment of Compton effect was like this much. Unlike to normal photoelectric effect, photoelectricity, as I told you, photoelectricity was done with ordinary visible light. Compton effect was done with X radiation. So, but ultimately, objective is same. X-ray is also electromagnetic wave. Only thing is that wavelength of X-ray is too small. Okay, and wavelength of it is 0.12 1 angstrom, and wavelength of X-ray visible light is thousands of angstrom. Visible region is 4,000 to 8,000 angstrom. But if you show, if you prove wave in photonic nature, ultimately it is proving, you are proving it for electromagnetic wave. So this was the experiment that electromagnetic radiation was coming in, and ultimately it was being scattered. This is a X-ray coming in the left side, and right side is a usual reflection. A red light is coming in. So we expected a scattering will take place because a wave is incident on a matter, and it was scattered also. But I asked you at that time also to to find out the difference between the right hand side picture, which is an example of a usual reflection or usual scattering or usual deviation of the ordinary light, and left hand side is Compton effect. Change is that here the wavelength of the incident beam and the scattering beam is different in the case of Compton effect, which is peculiar because in normal scattering, in normal reflection, wavelength does not vary. So again, classical physics could not explain it, because if it is a normal scattering process, wavelength should not change. So Compton has to explain it again with the photon concept, that it is the this is the Compton shift. Okay, you can see the picture. So Compton used photonic concept, that it is the photons coming in. He measured the photonic mass as in h nu by c square, photonic momentum h nu by c. So he is keeping photon with all the attributes of matter, mass, momentum, etc. So this experiment was essentially becoming therefore like this much. Photons are coming in, okay. It is being absorbed by, it is being colliding with the, you see, photon is a matter because you are defining photon with the property of mass and momentum. So matter photon is making collision with matter electron, and ultimately he thought that the nature of the collision is elastic. So if a photon is coming in, okay, with some energy, suppose I use different colors, you see, to show that wavelength is changing, okay. So photon is coming with some energy, some momentum, some mass, so it's a matter, and it is colliding with another matter electron elastically colliding. So ultimately wavelength is changing. Now this wavelength change was measured by Compton as this much, lambda c into 1 minus cosine alpha. So again, the major outcome of these two experiments of photoelectric effect and Compton effect is that both the experiments are telling waves can be photon-like. A known wave can show the property of matter. So property, light can show the property of photon. X-ray can show the property of photon. What are photons? Photons are like matter because that they are colliding with electron. They are defined by mass momentum. So what does it decipher? It implies a known wave can show the feature of matter. Now this idea actually further could be expressed like this much. That means this electromagnetic wave has therefore has got a, you see, in my class when I am teaching you photoelectric effect and Compton effect, I am telling that it is behaving like photons because it is colliding with electron. But you have got regular experiments of laser diffraction or interference class. There we define electromagnetic wave, okay, as the in those regular classes as interference, means say laser diffraction, where red light passes through the glass grating, so it gets diffracted. After diffraction they interfere, they superpose, and you see the spots in laser diffraction experiment. So what does it prove? It proves that in the physics practical class, when you do laser diffraction, red light is moving through the glass, getting bent, that is diffraction, followed by superposition. So I told you earlier also, superposition is exclusively wave property. Okay. Now, so light is wavy there. But in my class, now I am talking light is showing photonic property, photoelectric effect, Compton effect. So question is that light wave or electromagnetic wave, what it actually is? Is it a wave or matter? In my class, I am shouting it is photon. It is making collision with electron. And in your physics practical class, same me will change the word. No, light is a wave. Light is making diffraction. Light is making interference. Interference means superposition. Who superposes? Wave superposes. So same myself is talking different words in different time. In theory class, I am taking light is a stream of matter. In practical class, I am talking that light is a wave and it is making superposition, interference. Interference means superposition of waves. Question is that what is actually right? You cannot believe me. I am using the word, I'm changing my words. Now I am telling that light is a photon. Light is making collision. That means electromagnetic wave is a stream of photon making collision with electron. And same me, when I do laser diffraction experiment, I am telling, no, light is a wave. You see red light is passing through the glass grating, gets diffracted and making interference. Interference with superposition. That's why we get that pattern. So which one is right? What or why I am changing my words from class to class? Or I am actually doubting the character of light. Is it a wave or is it a matter? Answer is it is both. It has got a dual character. Sometimes it is wave-like and sometimes it is matter-like. So this dual nature of electromagnetic wave has got a name. This is called wave-particle duality. So wave-particle duality means electromagnetic wave has a dual character. In some experiments, it is matter-like, like Compton and photoelectric wave. In some other experiments, it is wave-like, like photoelectricity and like interference diffraction. But point is that in my class, you cannot use wave concept. Suppose, like, for example, you want to explain Compton effect with with wave concept, then it becomes a scattering process. X-ray was getting scattered, I initially thought. But if it is scattering, you cannot explain the change in color. Opposite is true. You cannot use my photon concept in your laser diffraction experiment of physics laboratory, because now which you did in first year days actually, that the light is, suppose photons are passing through the and getting diffracted, but the problem is that photons cannot superpose. Because photons are matter cannot, so photons can collide. So you cannot use your one theory, you cannot use the photonic theory in your practical class which you did in your first year lab, okay, and you cannot use wave theory in Compton effect. But you see, for some experiment I have to explain, use the photon theory, some experiment I have to use a wave theory. Question is that light actually what it is? Light is actually both, okay. In sometimes it is wave-like, sometimes it is matter-like, but it cannot show both the nature together. And you know, this is popularly called wave-particle duality. You see the animation going on there, wave-particle, wave-particle, wave-particle. So it is sometime wave, sometime material-like. So it's a beautiful experimental concept. You see, this entire idea of wave-particle duality is very significant in the development of physics. So this is something you should remember. That wave-particle duality means it's a story of betraying. In your school day, light was a wave, reflection, diffraction, and in first year, suddenly it is showing the photonic nature. I'm telling that light can be metal-like also. So this is a breakthrough in this development of quantum ideas, that the wave can be metal-like. Now, this idea was closely observed by scientists from, okay, Austria, whose name is Louis de Broglie. He observed that, did he observe? He observed this phenomena that wave can be metal-like. Earlier people thought waves and matters are different. Now this idea of wave particle duality tells you waves can be metal-like. Now de Broglie thought if a wave can be can sometimes show material property, if light can sometimes show photonic property, okay, opposite should also be true. That is, a matter should also show the property of a wave. That is, in Compton effect, electron is making collision with photon, so electron is a matter, electron has got a mass, okay. In their experiment, light is metal-like, there is photon-like, electron is also matter-like, they are colliding, because only matters can collide. Now, I am telling, what de Broglie is telling, if electron is matter-like in there will be some occasions in nature where electron should be wave-like. This is popularly called de Broglie hypothesis. Just imagine how everything came up. So wave particle duality tells us a wave can show the photonic nature, material nature. De Broglie is telling the opposite. Any matter, according to de Broglie, can show wavy nature. Actually, it will just follow photon concept. I told you at that time also, photonic mass is like h nu by c square. Photonic momentum is h nu by c. In that formula of momentum, if you slightly manipulate, c is equal to nu lambda formula, this gives you lambda, the wavelength of the photon, is equal to h by p. Okay, so you see here in this expression, p is the particle property and lambda is the wave property. So if you think, suppose you do not know light, you know photon. So photon is a matter with momentum p. So it is telling us if photon shows wave nature, its wavelength should be h by p. And that wavelength is the normal visible light wavelength. Now this has been a breakthrough concept. De Broglie has taken up the idea. He has taken up the idea, and it's a very important equation because you see this equation, right hand side is material nature, left hand side is wave nature, and this equation is a total punch to the classical people who thought that waves and matters are different. Now you see, so you've got a funny equation, you've got a bridge between the two concepts. Left hand side is a wavy nature, right hand side is a particle nature. Earlier people thought waves are different, matters are different. For people, for wave nature you use wavy theory, for electromagnetic theory or sound wave theory. For matter you use the mechanics. So two different worlds, now they are bridged. The wavy nature, wavelength, and particle nature momentum is connected by this equation. So this is the idea also taken by de Broglie. De Broglie told, therefore, any matter therefore moving, okay, can show the wavy nature, and if it shows wavy nature, its wavelength should be h by p. It's he has generalized whatever you see for photon. De Broglie actually generalized for any particle, any matter can show wavy nature. Okay, so this is the idea that if electron is moving like this, if it faces another electron, classically you know they will collide. But what de Broglie is telling, that electron can show the property of wave. Okay, that is a concept. Okay, it is electron is no more the matter, it is showing the property of wave. That is the proposal of de Broglie, and if it is wavy, it should have some wavelength, so de Broglie wavelength h by p. Now the idea of de Broglie actually was explained, it was an idea up to 1924, and later on it was actually, it was proved experimentally by Davison and Germer, you know. Davison and Germer has proved this wave nature of electron in 1927 through the famous Davison-Germer experiment, and ultimately these are electron waves. Okay, I told you in first year days also, they are not electron, that is called probability wave of electron. So here comes a very important question. Okay, how to prove that experimentally? Davison-Germer has proved it, I told you. Next question is that what makes this wave? It's a matter is showing wave nature, de Broglie is telling which kind of wave it is. To answer this question, to remind you, I'll just get into the very basic definition of wave. Wave means disturbance, wave means fluctuation, wave means variation. So these are the classical example of the wave. Say sound wave. Sound wave is a vibration of what? Matter making the body. Suppose I clap my hand. If I clap my hand, you see my hand is, the matter making my hands are vibrating. So it's a mechanical wave. Another wave is an electric wave. Electric field vibrates to make the wave. Another wave is magnetic wave, where magnetic field is changing to make the wave. Electromagnetic wave, where both electric and magnetic fields are vibrating. So question is that, you see, to make electromagnetic wave, two physically important variables are changing, electric and magnetic field. To make AC signal, electric wave, alternating current or voltage is changing. To make sound wave, matter is getting displaced, like spring, like vibration. So today we are talking about a new kind of, not today actually, last year I told you, just to remind you, we are talking about a new kind of wave, that is the material wave, the wave nature of the matter. Okay, so what does this wave means? Okay, because here in a quantum mechanics background, we talk about the very small particles like electrons moving in a metal. Okay, you see a lot of electrons are there in a metal, and you think practically your problem is in this microscopic world, because quantum mechanics is the physics of microscopic world, is that you cannot see the matter. Suppose electron orbiting around the nucleus. Okay, in those nucleus is the red balls and electron is the blue balls. Okay, in the right hand side picture, left hand side is actually opposite story. So what you notice here, that electrons are moving randomly, they are large in number. In a metal it happens. But if I take a piece of metal, can I see this electron motion? I can't, because electron is too tiny. Its size is too small to be located by our naked eye. So in a problem, when you'll be solving this electronic journey, your restriction is that you cannot see the electron. Okay, suppose electron is orbiting around the nucleus. Your problem is that you cannot see the electron, but electron is moving. Just like the way you see a big object and determine its position, we cannot do the same thing for electron. Okay, electron is moving, it can change, these are Bohr orbitals, all these things can happen. So your job, in order to explain the phenomena, but electron is moving, it's a mechanics problem, it's a rotational problem. Or you make it simple also, one-dimensional problem, electric motion also you can imagine. So this is a problem of mechanics, but your restriction, you cannot see the moving object. And any mechanics begins by answering the question, two WH questions, where and when. So how do you answer the question where the electron is at a given point of time? So how do you answer that question? It's a very funny and tricky area. So then I in first year I told you in terms of me. Suppose I am taking your class. Okay, where do you find me inside your class most of the time? Most of the time you will find me if I take your class of say 1 hour normal traditional class, and if I work on the board, most of the time you will find me in front of the board. So if you for a 1 hour span, if you take say 100 photos of me, in 80 photos you will find me in front of the board, blackboard or whiteboard, whatever it may be. So probability or chance of finding me, if you plot it in a scale in your classroom, the chance of finding me is higher close to blackboard, and to some other region it is lower, and to some corner maybe it is 0. So if you try to plot it in a graph, some chance of finding me inside your classroom from position to position will vary. It is higher in the board, in front of board, and lower in front of the away from the board. So basically something will vary. Somewhere it will high, somewhere it is low. Any variation, any change makes a wave. So there it will make a wave of myself. But that is not with me because I am standing separated. So that wave is a probability wave of me, a chance of finding me. Now if you're in the virtual board now, if I give you that graph, just by looking at the graph, you can realize where you find me most of the time when I take a traditional class. So there's also something is varying. In front of blackboard, chance of finding me is high, chance of finding me is low, some corner it is 0. Any variation makes a wave. So that makes a wave of chances or wave of probabilities. So that is the similarly when electron orbits also, you have to take chance to find out the electron. Okay, some are chances may be just like me, some are chance of finding may be higher, some are chance of finding in the electron will lower. So chance will vary. So with chances you define a wave, because wave means variation, fluctuation, anything. So that variation and fluctuation will make a wave of chance of finding electron or probability wave of the electron. So the wave that I talk in a quantum mechanics course is not the wave like light and sound. It's a mathematical wave, probability of finding the matter. Obviously, I am a big object. You don't to see me. You don't need a wave. You don't have to take a chance. But electron is a microscopic object. That's why it is told that this wavy nature of matter is more prominent for the small objects. Okay, as I have written here. Okay, for small objects, so you can see it. Okay, just like electron orbiting on nucleus, you see so many electrons are moving. Okay, but to you it is difficult for you to know where the electron is. You take chances to look at the right hand side pictures. Okay, yes, if you look at the right hand side picture, you notice. Okay, if you look at the right hand side picture, you just see. Okay, as the electron is changing its position, okay, the chance of finding the electron is along in one dimension. If you plot it, chance of finding the electron, you see, if you look here, chance of finding the electron is changing. Okay, it is varying. Here in the bottom picture, at a given point you see it is changing with time. Okay, sometime it is high, sometime it is low. So if it is high, you may predict electron may be there. If it is low, electron may not be there. So to know, so basically you see, depending on the where electron is, okay, or what is the chance of finding electron at a given point, it is all varying. Chances are varying, and that variation is forming a wave. Okay, in my picture it is changing every time. Okay, so that is the wave we are talking about in quantum mechanics. That wave is not electron. That is a probability of finding the electron. That is called probability wave. Okay, so this is the basic concept you should remember. In quantum mechanics, we talk about wave nature of matter. That is not a physical wave. That is a probability wave, mathematical wave. Because I cannot see the matter, I take a chance to find out the electron at a given point. At a given point, chances will vary, and that variation makes wave. That is called probability wave of the electron. Probability of finding the electron, like that. Okay. Okay. So this is the way we can see these are the various probability waves of electron. Okay, that is not electron. There's a chance of, just like say s orbital, p orbital, everything we say, these are not electron. These are the chance of finding the electron. You see, when electron will orbiting around the nucleus, chance of finding electron will vary. Okay, so that makes the wave. Just like s wave, p wave, you learned in school syllabus. Okay, s wave means you are thinking electron may be available over a probability of finding the electron over a sphere. P wave means over a dumbbell like that. Hybridization concept. That means you are thinking that SP hybridization. That is the Hybridized means over the overall that region, okay, in the superposed region, what is the chance of finding the electron? So these are actually in chemistry courses you have already applied this without knowing many things. So basically that ASP are not electron, they are the probability waves of electron. Okay, you can see these are all probability waves of electron. You see, suppose a matter is moving. So at a given point C, that is a vertical position, you see as the matter is moving, chance of finding the matter is changing. Okay, as the matter is moving. Okay, because it is moving. That's a very easy common concept. If you only stick to the point, say the vertical line, at that point, how the red ball is moving. You see, when the ball is approaching, it is at a peak, and when the ball is moving, it is at a dip. So what is at a peak and dip? Chance of finding the objects. So it is varying. So it is making a wave. So this is the wave we are talking about. So quantum mechanical wave is not like light and sound. It's a wave of probabilities. Because I cannot see the matter, I have to take chance to find out the matter. So this is called the wave of probabilities. Now, you see, if you look at the picture, as the bat ball is moving, this is one of the problems that you do in a quantum mechanics course. Very important problem. Almost every year comes in examination. So this problem, you see, this makes the wave as the matter is moving. But you see, this wavy parameter can be plus and minus. But as everybody of us know, probability cannot be negative. So there is a prescription of mathematics teachers of you that you take the variable you just consider as a function, just like here it is almost forming a sine function, and you take the square of that function to get the probability. This is the Born's idea of a German scientist called Max Born's interpretation. Okay, just like here you see the picture, as the matter is moving, okay, it can become plus minus, but the chi square, the probability square, wave square, at a given point, the probability of finding the particle is given by mod chi square. That is positive every time. So this is a very important idea. So for the takeaway from the next class, wave particle duality, that is wave can be matter like. De Broglie hypothesis, matter can be wave like. Okay, that wave nature is the wave of probability. That wave we talk about is quantum mechanics class is the probability wave or a wave of chances. Wavelength is h by p. Now I am telling the chance cannot be negative, probability cannot be negative. So that variable parameter we call just as a mathematical function psi. Mod psi square gives the probability of finding the particle, and total probability is given by is obviously 1. That is mod psi square large means object is there, or mod psi square small object is not there. Total probability has to be 1. So this is the summary of first year discussion. Now next class, okay, actually these I made a long summary for you to help. I hope it will be helpful for you. You just see this video many times. If you forget, it will be almost in a capsule. I have put your entire first year details. Okay, so basically your takeaway is that most important parameter in your class is that a mathematical function psi, that is representing the wave nature of the matter in quantum mechanics. You know, 4 things can happen in nature. A matter can be matter-like, collision. Wave can be wave-like, superposition. Okay, wave can be matter-like, photon concept, and matter can be wave-like. Or that is the probability wave concept what De Broglie told. That is something you never heard, and that is the concept we have developed in the entire study of quantum mechanics 1. A matter can be wave-like, and that wave is a probability wave described by a function psi. So this is something you do not know, or you just know from your first year days maybe. So with that an angle, actually almost entire of the latest of the physics, entire solid state physics, quantum mechanics 2 that we will be learning, nanomaterials, whatever you will be learning, all modern concepts of physics are application of these ideas only. Okay, so basically we will do those applications starting from the next class. Okay, I hope I have made a long recapitulation. It will be helpful for you. Okay, so we'll discuss that. Okay, how you use this idea, whatever be the ideas you have. Main idea, matter is wavy, wave nature is wave of chances described by the mathematical function psi. Mod psi square actually gives the where the object is. The basic question of mechanics, where the object is, psi square. Mod psi square gives you that idea. So getting psi or knowing psi, the wave function is very important. So we have to learn some technique now how to deal with this new world. We'll do that for the next class. Thank you.